So in this video we will study the second type of improper integrals. Now we will do it through a definition. So we have the following situation that we have a continuous function f on the left open interval a to b, where f of x converges to plus or minus infinity as x approaches a from the right. So the left point of the interval is approached from the right clearly. And what we do is to define the improper integral from a to b as a limit over a sequence of definite integrals. We define it as the limit for c approaching a from the right of the definite integral of f over the interval c up to b. And we call this limit I. Now again we can have two situations. The limit I exists and is finite. Then we call this improper integral convergent, and we give it the value I. And in case the limit does not exist, then we call this improper integral, we call it divergent. Can define the situation where f of x converges to plus or minus infinity at the right point of the interval in a similar way. Okay, let me give some examples. So suppose that we wish to calculate the integral of the function 1 over x over the interval 0, 1. Now clearly if we look at the values of this function at 0 and 1, well then we see that at 1 it's well defined, but at 0 it is not. And in particular, if the function value, if x converges from the right to 0, then the function value converges to infinity. Okay, so let us try to calculate the improper integral. So we do it according to the definition. So we take the limit for c approaching 0 from the right of the integral over the interval 0, c up to 1 of the function 1 over x. Now we know that the primitive of the function 1 over x is equal to the natural logarithm of x in absolute value. We have to compute it at the value at c, at x equals c and x equals 1, and we have to take the limit for c approaching 0 from the right. So what we get then is that this equals the logarithm of 1, which is 0, minus the logarithm of c in absolute value, but c is positive, so we get the natural logarithm of c, and we have to compute the limit as c tends to 0 from the right, and since the logarithm converges to minus infinity as c tends to 0, and of course we have to subtract the value of ln c, we get that the minus ln c converges to plus infinity. So we are in the case that the limit doesn't exist, and we have a divergent improper integral. Now we have another example where the corresponding function behaves itself a little bit nicer. So we have the same integration interval, but now we want to compute the definite integral of the function 1 over square root of x. So let us again write the formal definition of this improper integral. And now we calculate the primitive of the function 1 over square root of x, which is equal to 2 square root of x. We evaluate it at the points c and 1, and we take the limit for c approaching 0 from the right. And what we get is the difference of 2 times square root of 1 and 2 times square root of c. We take the limit and we see that we get that the 2 times 1 minus 2 times square root of 0 is 0. So we get 2 as an answer, and so we have a convergent improper integral with value equal to 2. Now what you see here is that we have to take limits, and it is good to mention some important limit rules. You can find these on pages 73 and pages 183 of the book. And the main limit rules which I think are useful for you are the cases where we have two polynomials, p and q, and we wish to compute the limit for x approaching plus or minus infinity of the quotient of these two polynomials. Now suppose then what we get is that this limit is equal to 0 if the degree of polynomial in the numerator, so if the degree of p is smaller than the degree of the polynomial in the denominator, because this pulls it down to 0, and it is equal to so let me put absolute signs because we get the same result there. So this limit is equal to plus infinity if the degree of the polynomial in the numerator is larger than the degree of the polynomial in the denominator. Now if the degrees are both equal, then you have to be a little bit more careful. Of course, we won't discuss that here. Another important limit or other important limit results are the following ones: that if we take a number a that is positive, then if we want to consider the limit of x to infinity of x to the power a divided by e to the x, then we get 0. Of course, if we compute the limit of x to infinity of the natural logarithm of x divided by x to the power a, then we get 0 as well. If we compute the limit for x to minus infinity of the function x in absolute value to the a multiplied by e to the minus x, then we get 0. And if we let x approach 0 from the right, and we compute the limit for x to the power a multiplied by the natural logarithm of x, then we get 0 as well.